Hello and welcome to my presentation on the AI Smart Parking System in Real-Time Monitor. My name is Aino Maria binti Abdul Muttalib, presenting University Science Malaysia. I would like to extend my deep gratitude to my supervisor, Dr. Siti Hazanti binti Muhammad Hashim, for her continuously guidance and support throughout the development of this project. Today, I will be walking you through the software. First approach to modernize urban mobility and solving one of the most persistent frustrations for driver today, which is parking. To understand the value of this project, first we need to look at the current landscape of the smart parking. Right now, the dramatic increase in the city traffic and the vehicles ownership cause a major congestion, which is driven heavily by a driver continuously cycling just to find an open parking space. Currently, the traditional smart parking rely on outdated infrastructure. This system depends on expensive physical IoT sensors such as ultrasonic or ground detector. Unfortunately, these physical sensors are costly to install, challenging to maintain, and have very limited scalability. To solve this, our projects introduce the AI paradigm shift. We are moving forward a software-first solution using a computer vision replace the physical hardware sensor entirely. To bring us directly to our core problem statement, which is a divide by two main areas. First, let's look at the traffic and emissions. Cruising for the parking heavily worse urban consumptions. This behavior wastes valuable driver time. Firstly, increase fuel consumptions and directly contribute to a large carbon footprint in a busy city center. Second is the issue of high hardware costs. Existing systems require at least one physical IoT sensor per parking lot. These introductions massive instantly deploy a cost and create a constant ongoing hardware maintenance overhead for a facilities operator. To overcome this challenge, this project was built upon three primary objectives. First, its objective is a real-time occupancy detection. We aim to design a reliable system that detects and identifies parking space availability in a real time using a computer vision, camera feeds rather than a physical sensor. Our second objective is to implement deep learning. We are implementing a machine learning models to detect vehicles and predict a parking occupancy trend using both current and historical data. And the third and the last one objective is a multi-location centralization. We want to provide a user with accessibility, real-time information on parking availability across a different location, all from a single platform. Our proposed solution relies on AI-powered computer visions. Our solutions completely replace a physical ground sensor with a software-oriented approach, utilizing existing CCTV infrastructure. By developing the lightweight YOLO deep learning models, the system accurately detects the vehicles and classify the parking lots as occupied or available in real time. One of the most significant advantages of this approach is hardware efficiency. This allows the system to function flawless and cost efficiently, even on a standard CPU hardware without a required heavy CPU investment. To ensure seamless operations, the system is divided into four modules. First is a user management. User management provides an interactive dashboard for a driver to view a real-time parking availability and predict occupancy without any required registrations. Second is a parking detections. Parking detection modules act as the brain of the operations. It uses a YOLO and FSM logic to detect vehicles and update slot status reliabilities direct from the video streams. And the third is payment modules. Payment modules is handle automate fee consumptions based on accurate parking durations, supporting quick and secure digital QR code payment. And the last one is the admin management. Admin management modules offer centralized control to administrator to monitor CCTV streams, manage fee rates, and generate the analytical facilities report. Here is a closer look at our system architecture, which is operating in a continuously linear pipeline. Step 1 is a camera feeds. Camera feeds is a capture video input process frame by frame. For this prototype, we utilize a pre-record parking video. Step 2 is a video processing. In the video processing, we use OpenCV to optimize input via frame extractions, resizing, normalization to ensure the high detection accuracy. Step 3 is an AI detection engine. Our YOLO models act as a core component that identify the vehicles and determine the parking lot status occupied or available using the bounding box. Okay, step 4 is a cloud database which managed by Supabase, which store and synchronize the real-time slot status, parking durations, and transactions data. And the step 5, the last step, is the web interface, which is built with a Streamlit. It serves as a dual view dashboard, provide a real-time availability for a driver and a comprehensive monitor for the administrator. By shifting to this software architecture, we identify a few major benefits. First is the high cost efficiency. It eliminates the need of the expensive physical IoT sensor, reducing the installation and maintenance overhead significantly. Second is the eco-friendly. The system decreases unnecessary cruising times, actively reducing the carbon emission and alleviating local traffic congestions. And the last one is the maximize user convenience, which it empowers the driver with a real-time availability tracking and seamless automate the digital checkout experience. Beyond the technical achievement, this project presents a strong entrepreneurship opportunity. The AI smart parking system is designed not just a function technical prototype, but is a highly scalable and cost-effective product that are ready to be extended for a pre-commercialized in the urban markets. It offers a cost-effective deployment by limiting the heavy capitals and maintenance costs of the standard one sensor per slot hardware by utilizing existing camera CCTV infrastructure. The software-first approach allows for high scalability, ensuring the seamless expansion across a driver's environment from a university campus to a large commercial complex. Furthermore, it's already to a market solutions. It features a fully integrated digital payment module with a QR pay and automate a fee calculation system, providing an immediate framework for revenue generations by addressing a critical urban pain point such as a traffic congestion and high carbon emissions. Instead, it into a strong market demand, making it highly interactive for a smart parking initiative. To bring this all together, I will now walk you through a system demonstration. In this segment, I will be showing the real-time AI detection processing live frames and navigating through the Streamlit dashboard integration to show how a user and admin interacts with the data, and the final showcasing the automated QR payment flow. We will start by looking at the initial step of the user dashboard before our AI engine is active. As we select Kusbe Mall and enter the facilities, take a look at a facilities overview. You can see that the system currently show 131 available space with a 0 occupancy rate. If we scroll through the different parking levels like W1, W3A, 5, 7, and 8, every single parking slot is marked in green, indicate that they are completely available parking. We are showing you this baseline to demonstrate how the system dynamically update once the AI take over. Now let's move behind the scene to our backend environment in VS Code. To bring the system online, we execute our primary manager script in the terminal. Watch closely at the script initialize. First, it defines as a register all the parking lot across our multiple zone, which is W1, 3A, 5, 7, 8 and M10. Next is establish the secure real-time the connection to our supervised cloud database. Finally, is load our YOLO deep learning models for each camera zones. These initializations ensure that all the models are perfectly synchronized before the video feed start processing. With the back end running, the system began pulling the live video feed of each parking zone. Immediately, the YOLO object detection model goes to work. On the screen, you can see that AI actively scanning every frame. In the map bounding box over the parking area, the screen box confirms the slot is empty, while the red box detects the vehicles and mark it as occupies. Simultaneously, if you look at the terminal, you can see the system locking this as the state change. For example, update the slot W1, W128 to occupy or more. Our final state logic ensure that these detection are stable before pushing them to the database. Let's back to the Streamlit user dashboard to see the result. If you notice the change, the system is completely synchronized with the AI. The facilities overview now show 85% occupancy rate with the availability space dropping to 19. As we look at the parking layout, it's not longer green. The dashboard is now populate the red slot, reflecting the exact real-time occupancy data captured by our camera. Driver can use the interface to quickly pinpoint the remaining green slot across the level. When the driver is ready to leave, they simply scroll down to the secure payment portal. Watch as we enter the specific parking lots ID such as W105. The system instantly queries the database, retrieve the exact entry time and calculating the parking duration down to the seconds. It applies our base rate and the time base fee to generate the total due. The user then click the process to the QR payment button, scan the generate QR code with their mobile banking apps and successfully check out. A digital access pass is immediately appear and confirming the barrier will open. Now, we will explore the system from the facilities manager perspective. We navigate to the admin portal and log in using our secure administrator credentials. Once inside the admin consoles, the manager gets top-down view of the facilities operations. The live facilities monitoring tab is particularly powerful. Here, the admin can view the live parking grid along the CCTV stream view. This dual view setup allows the operator to cross-reference the digital layout with an actual camera feed with a visually verify that the AI is detecting the car accurately. Next, we move to the Setting and Configurations tab. These modules give the admin complete control over the system without needing to touch any code. They can update a facility info or easily adjust the parking fee structure. For example, if the operator changes the rate per second, it immediately applies to all the future checkouts. Below that is the manual slot update tool. While the AI handle almost everything automatically, this feature acts as an override. By entering the slot ID and manually switch its status, the admin can instantly force the update to the database, which ensure the maximum accuracy if the camera view have a problem. Finally, we navigate to the Generate Report tab. The data analytic is crucial for commercial parking facilities. The admin needs to select the specific start and end date from the calendar and click the Generate Financial and Usage Reports buttons. The system instantly acquire the database and compile the data. It provides a clear report summary detailing the total car park, total revenue generated, and the average parking durations. Below this, a comprehensive transaction log lists every single parking session, complete with the timestamp and the payment status. This provides the operator with the exact insight they need to manage to optimize their facilities. That's conclude the demonstration and my presentation about the AI smart parking system. So thank you for your attention and see you again.